What we're going to be doing today is reviewing the parts of the volcano, the different types of volcanoes, different types of lava, the different plutonic structures that you might find underground underneath a volcano, and we'll also make some connections back to igneous rocks and where those are formed. So we're going to do kind of like a picture, and we'll be labeling some things off to the side. So you should have a blank piece of paper in front of you. I always turn mine landscape just because that's the way my board goes. So you can decide which way you'd like yours to go accordingly. So first, we need to draw just a basic, generic volcano. So we know that that means we need a pen. There we go. And we need a cone with a crater. And down the other side. We're going to add a little bit to this so that we can put in some of our plutonic structures. We'll put in a little bump over here, and we'll say that that's going to be the end of our picture on that side. And on this side, we'll have the volcano go down a little bit further, and we'll call that the end of our picture down at the bottom. On this right-hand side here, we're going to add some water also, because we know that volcanoes often form next to or in oceans. So that's going to be like our ocean on the other side. Okay, so let's label some of the parts of the volcano. Of course, this part up here is the crater. The opening itself is called the vent. And then, if it's going to be a volcano, we'll need to put some lava inside. So we'll have a big magma chamber down at the bottom. And we're doing plutonic structures too, so we'll make room for some of those as we draw in our magma chamber. All the way up to the vent. And on this side, we'll have a little fissure or a crack in the rock in the volcano. And again, all the way up to the vent. If this volcano were to have had its magma hardened underneath, so if it were no longer an active volcano or the magma had hardened, this part down here would be the batholith. And then we would have the mushroom-shaped one right here, would be the laccolith. A vertical crack that's filled with magma is a dike, and a horizontal crack that's filled with magma that's hardened is a sill. And there's most of our plutonic structures. We could add a stock to this, which would be a small batholith. We could put that down here. If the vent hardened, if the magma up in the neck hardened, and then the cone was eroded away, this would be the volcanic neck up here. But we'd have to take the cone away for that to be true. I think that pretty much covers our plutonic shapes. Okay, so what happens when the magma actually comes out of the volcano? Depending on what kind of magma it is, you might have a very runny lava flow that would just flow down the side until it hardened, which it definitely would do if it hit the ocean, since the ocean water is quite cold compared to magma. Or If it was more of a pyroclastic eruption, you might have little pieces of rock and ash and flying up the top of the volcano here. All those different sizes of tephra that we talked about. We talked about ash and how fine of particles it is. We talked about that also being called lapilli. We talked about the larger pieces being called bombs and blocks. So depending on the size of the pieces, that tells you what kind of tephra you've got. Okay, so types of volcanoes then. We don't know exactly what kind of volcano this is. We've drawn just kind of a generic shape here, but we could, off to the side, list some of our types of volcanoes and characteristics that go with them. So we'll start with the cinder cone. Cinder cones have very steep sides, and like that, although they are not as tall as composites. They typically have felsic lava, which is also sometimes called rhyolitic. They typically have pyroclastic eruptions, which means you would have lots of tephra and ash, lots of explosive gases, not very much lava itself coming out. And that is partially due to the fact that they typically form under continental crust. Continental crust is high in silica, and that makes the magma very viscous and sticky, traps the gases, and makes it very explosive. So this was our first kind of volcano. Our second kind was a shield. They're called shield volcanoes because they look like a warrior's shield when you tilt them on their side or look at it from the side, kind of like that. These are the largest in terms of area that's covered, although they are not the tallest. These are usually made from mafic, which is sometimes called basaltic lava. And they often form at divergent boundaries or hotspots like Hawaii. And their eruptions are usually non-pyroclastic because they usually form under ocean crust, and ocean crust is high in basalt, which means it's low in silica, so it's not very sticky. It doesn't trap gases, and that makes the eruption not very explosive. Last kind is composite. These are the ones that you typically think of when you think of a volcano. Pretty tall, fairly steep, sometimes they're snow covered. Composite volcanoes can have either or both kind of lavas because they form typically at subduction boundaries, which means often they have access to both oceanic crust and continental crust. And having both kinds of crust means you get both kinds of eruptions. Sometimes it will be pyroclastic, sometimes it will be non-pyroclastic. It just depends on what kind of rock's being melted at that time. Okay, let's make a connection back to our igneous rocks now. All those igneous rocks that we talked about a couple months ago form in different parts of the volcano, and it has to do with how long they have to cool. So you might remember, if they have a long time to cool, that they make large crystals, and this is my artist's rendition of what large crystals would look like. So if you have large crystals, then maybe I better label that so you know what that is. These are large crystals. Those rocks would have been either granite or gabbro. You might remember that granite was from felsic lava because it was typically lighter colored. Gabbro was from mafic lava because it was typically darker colored. And the rocks that form inside the volcano we labeled as intrusive. If they form outside of the volcano, then we labeled them as extrusive, because they formed outside the earth. If they were exploded off the top with a lot of gases, then you might produce pumice or scoria. Those were the ones with holes in them from the trapped gases as the lava hardens. Pumice was felsic, it was light colored. Scoria was mafic, it was dark colored. If the lava came out and ran down the sides, but still cooled pretty quickly, then you might get some smaller crystals. And again, I'll label my artist's rendition here. These are supposed to be small crystals, which means rocks that formed here would be like the rhyolite that we saw and the basalt that we saw. Rhyolite was felsic, it was light colored. Basalt was mafic, it was dark colored. If that rock cools so quickly that it doesn't have time to form crystals, which might be along here, and we'll make it black because we know that that's the color of this rock, you would get obsidian. And that would be at both places. Sometimes it forms when it hits the water because it cools so quickly. Other times it might form just kind of next to the water, just outside the volcano. And we know that even though it's black, obsidian is felsic. That was kind of our exception to the color rule. All of these rocks that formed outside the volcano we labeled as extrusive. And there you have volcanoes in a nutshell. We've gone over our plutonic features. We've gone over our types of volcanoes, types of lava, where they're found, types of boundaries that they're associated with, types of eruptions, what each volcano looks like. We've talked about different types of tephra. We've talked about the parts of the volcano. And we've connected back to igneous rocks that we talked about a couple of months ago. Please study for your test that is coming up. And that is it for today.